the midterm review was like perfect for the homework.
Oh, I figured it would be just because the problem two on the homework is very similar to what I'm the kinds of questions I'm going to ask you on the midterm. So um,
Yeah, like I kind of understood from like the previous lectures, but like it was kind of hard going back and forth because I write my notes on my laptop with
mhm.
the pen.
Yeah.
Kind of hard switching back and forth. I'm like, okay, I saw this here, and then like literally like connecting the dots, and then like you literally just put everything together. And I was like, I was just it was great.
I'm glad it helped.
Yeah, thank you for that.
Yeah. Yeah, because I figured, I know you guys will be studying for the midterm at the same time as this homework, so I might as well, help you prepare for the midterm while doing the homework at the same time. Because it is kind of a tight schedule. So that's why I kind of wrote that question too, to be, to prepare you for that.
I feel pretty confident now.
That's good. That's good. I already fed her. I don't know what she's talking about. I just went over the railing just to tell her to shut up because I fed her like literally 20 minutes ago. I'm glad the midterm review was helpful. I never said the exam would be easy.
Hey, Professor.
Hey,
Well, midterm is going to cover homeworks 1 through 3, right?
correct. Yeah. Mm-hmm.
Okay, thank you.
Mm-hmm.
And when's homework 4 due?
I haven't posted it yet, but I thought I'd give you guys a break after the exam, so I probably won't post homework 4 until next week.
Awesome, thank you.
Yep. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing on the eve of the exam? I guess 2 days prior, so the lecture eve, I guess. So everyone's working on homework 3 right now, and I got a lot of questions about it over the weekend. But hopefully, at least for problem 2, hopefully, the midterm review video that I posted was helpful. And so, I wrote that problem 2 on homework 3, very carefully, because that's kind of, that's kind of the level of what I would expect you to do on the exam, because the exam's not going to involve any MATLAB. And so it's just going to be, just mostly just short answer questions and just, and just writing things down by hand. And so, I designed that problem 2 on the homework just to kind of give you practice with that. So if you can do, problem 2 on the previous homework, both for the 1D and the 2D problem, and you go through the midterm review video, I think you're going to be in great shape for the exam, at least for the problem solving questions, of course. And then there's also, all the short answer questions that you need to know as well. How long is the exam going to be? So the exam's going to be basically 3 short answer questions. And so it's going to be 3 questions where you can basically just type up your answers into the browser, and then 2 problem solving questions. So the 2 questions would be basically just similar to problem 2 on the last homework. And so I'll tell you right now that there's going to be a 1D problem and a 2D problem on there. So there'll be a 1D problem where I'm going to ask you to write out basically the system of equations, and then a 2D problem where you would have to write out the equations like that too. Yeah.
Professor.
Yep.
So for the coefficient, should I simplify them or should I keep them while trying to write that?
You should simplify them. So you should definitely, I'm going to give you numbers in for, the diffusion coefficient and for the grid spacing, all that stuff. So you should definitely plug in for those and get numbers for everything.
Okay, thank you.
How hard did I make it? So the so each of the problem solving questions, like the problem 1 and problem 2, they fit on 1 sheet of paper for me, and so that was kind of my litmus test, and each of those only took me about 5 minutes to do. Yeah. There'll be 3 short answers. Yeah. It will be like problem 2 on homework 3. So the homework that you're turning in today, problem 2 is basically what I'm going to expect you to do for the exam. So. They're not going to be they're not going to be exactly like homework 3. So don't come in and expect to just copy that in, but it's going to be very, very similar to that. So it's 3 short answers, and then and then the problem solving, the amount of time to write it down shouldn't be an issue. So it should be more like it should more just test you on whether you know how to derive these equations. The shape of the grid will be a square. Yes, I'm not gonna throw anything weird at you. So it's going to be a square.
Mm-hmm. Will the exam be proctored?
You can come into the Zoom session if you want, but I'm not going to watch you guys. I personally think that's kind of weird, because it's you're taking this exam in your own homes, and I want to avoid looking into your homes if I can avoid it, because I feel like that's your private space, so and so I won't require you that you come onto the Zoom call, but I will be here on the Zoom lecture call, so if you want to come in and ask questions during that time, type of course, so don't turn on your mic, then I'll be here, but it's not a requirement. And so the only thing is that you'll have 90 minutes to complete the exam, so from 5:30 to 7, by 7 o'clock you should have everything uploaded onto Canvas, but it's not going to be proctored. Yeah. Okay. And I'll be available on by email and Discord too. And so if you would rather ask me questions on there, then that's fine too. Yep. All right. Any questions on any of that? Okay. All right, so let's go ahead and continue where we left off on last Wednesday. And so last Wednesday, we were doing our lecture notes on time marching schemes. And so remember, time marching schemes are not going to be on the exam. Homework 3 is the cutoff for for the midterm. But this is stuff we're going to need going forward, especially for your final project. So your final project is going to be an unsteady problem, and so you're going to need to know how to march this forward in time. And so I think explicitly, what we left off on was we were doing an example. And so our example was a simple unsteady diffusion problem. And so, you know, our governing equation looked like this. And so we had partial phi partial t is equal to 3 times partial squared phi partial x squared. Okay. And then with this, we had the following boundary conditions. And so our boundary conditions, we had a Dirichlet boundary condition on the left side. And so we had phi of x is equal to 0 and t is equal to 1. And then our other boundary condition on the other side, we have d phi dx at x is equal to 1 and t, this is equal to 2. Right? Okay. And so I got some questions about this over the weekend. So let me kind of address this right now. And so for this, for these kinds of problems, you know, usually I give you a domain that looks like this for 1D. Right? And so usually the domain is set from 0 is less than x, which is less than 1. And so when I tell you that a boundary condition is that x is equal to 1, that basically tells you that's on the right side of the domain. So you know, the rightmost node. Okay? So that's the boundary conditions. And we also have our initial condition here. And so our initial condition is phi of x at t is equal to 0. And so this is the, you know, the phi value at the initial time. And we're going to start with an initial, a 0 initial condition. So we're going to start with 0 everywhere. Okay. And so what we did last time was we, you know, using a grid of 5 points, what I wanted you to do was I wanted you to march this forward in time or apply the explicit Euler you know, scheme with a time step size of 0.1. Right. And then, you know, with a grid of 5 points, you know, our delta x is equal to 0.25 here. Okay. And so I'm not going to go through the whole derivation of explicit Euler again, just because it's kind of lengthy. But, you know, I do want to show you kind of the end result. Right. And so after you do all this, what you get is the following, you know, matrix multiplication system. So I won't call it a system of equations because it's not that. But, you know, we do have to perform some matrix multiplication. Because remember, you know, whenever we have a time marching scheme, what we always want to solve for is we want to solve for all the solution values at the next time. And so we had a system that looks like this. And so we had the phi values at each of the grid points. And so since we have 5 grid points, we're going to have 5 phi values, right? And so this is basically what they represent. Okay. And this is going to be at n plus 1, right? So remember, n plus 1 means the next time step, right? Because we're solving these equations one step at a time. Okay. And this is going to be equal to a coefficient matrix. And so this is, you know, the coefficients that we obtain by applying explicit Euler. And for this problem, it's we got the following coefficients. Okay, and then we have 0, minus 8.6, 4.8, 0, 0, and 0, 4.8, negative 8.6, 4.8, 0, 0, 0, 4.8, minus 8.6, 1, and 0, 0, 0, 4.8, 0. And then what we had here was all of our phi values. Okay, at the current time step. And so this is at time step n. Okay. And remember, the solution at the current time step is known. Okay. And then to this, we have an additional vector out here, which are all the extra terms that don't have phi involved. Right? And so for this problem, we had 1, 1, 1, 0, 0, 0, 0.5. Okay. Right. And this equation is what we can use to advance this, what we can say, advance this system forward in time. Okay? Because now that we have unsteady problems, when we solve for all the phi values at these nodes, okay? And so when we solve for phi 1, 2, 3, 4, and 5, right? Normally when we solve these, or up to this point when we solve these, we solve for just one static value for phi, right? Because it was a steady problem. Now what we're saying is that, because we're unsteady, all these phi values here, all of them can change with time, right? And so what we want to do is we want to basically solve for all of these values for phi as a function of time. Okay. And so to do that, we're going to plug in first going to plug in our initial condition here, right? Which is going to be all zeros. And then, once we solve for the first step, then we're going to plug our solution from the first step in for back over here, and then kind of just repeat this process. Right? And so I think it's a little bit easier for me to kind of show you the code associated with this. And so, I have that kind of prepped right here, and I have posted this this code onto Canvas as well. But for now, you can just kind of follow along, and then kind of download the code for you to try later on. Okay, so are there any questions on this? This is just kind of a recap of what we covered last time. Okay, all right. So let me go ahead and switch to my laptop screen. And so this is the code that's on Canvas right now. And so actually, if you go to Canvas, it'll be kind of this script right here. So this is the explicit time marching MATLAB example. But again, you don't have to download it. I just want you to kind of watch right now and just kind of follow along. Okay. And so the first thing we have to define here is our coefficient matrix. So let me bring this the notes back up here just so you can see it at the same time. Okay, so I'm defining this matrix right here, which I just shown in the notes. Okay, and so you can see here we start with the zeros matrix and we set all the values accordingly. Don't worry about this one yet, and so we'll cover this a bit later. Okay, and then from here we have to assign this vector now. So in this vector we just have 1 and 0.5. Okay, and you can see here I've created two containers here. Okay? And so one is sol next and the other is sol cur. Okay? And so sol next, we're going to use this variable to contain our solution at the next, which is the n+1 time step. Okay. Meanwhile, we're going to use sol cur, and this is going to contain our solution at the current or the n time step. Okay. Okay. And then so from this, we can start to actually advance this in time because we're going to basically solve this one time step at a time, right? And so from here, this NT, you can basically, this is the number of time steps that we want to solve the equation for. Okay. And then here, I'm basically preparing it for plotting. And so I'm creating the, the figure and I'm getting ready to plot it. And so what I'm going to do here is basically, I'm going to march this system forward in time. And each time, I'm going to, plot the solution. Okay. And so what you'll see when I run this code is you should see kind of several curves kind of lined on top of each other. And those curves are, how the system is changing with time. So you can almost think of that as like several snapshots at different times. Okay. So let me go ahead and run this code. Right. And what you'll see is this. Okay. Right. And so, each of the different colors here represent the solution at different time steps, and this green one is the most recent one. Okay, and so and you can see here the solution is varying between about -8,000 to about 10,000. Okay, and so I will say that this solution is not good. Okay, because what this solution that we're viewing right here should look familiar to you guys to some extent. It looks like Simpsons clown hair. It kind of does. This solution should look very similar to, the unit that we just finished on convection, as in this solution here is unstable. Okay. And so this is kind of the risk that you run when you use the explicit Euler time integration scheme, is that you run the risk of having unstable equations, right? Which is not good. Okay? And so, just like we saw in convection, when you have an unstable solution, you kind of have two options here on what you can do, right? And so one option that you can do is you can simply just refine the problem, okay? And so for unsteady problems, this means not making delta x smaller, but by making delta t smaller, right? And so we can change the problem such that instead of using a time step of 0.1, we can use a time step of 0.01. And that's what I've done for you here. So I basically recomputed this A matrix to use a smaller time step size. And that makes the coefficients kind of smaller, just like this, okay? Right, and so let me go ahead and try running that for you, right? And so in this problem, I've already kind of done the calculations for you. And so let me change this A matrix right here to A fine, okay? And so now this is using a smaller time step. And when I run this problem, you should see the actual solution, right? Okay. And so you can see here, this solution is no longer unstable. And so now we're stable, right? So you can see here, we start with this kind of light blue one. And as time advances, the solution kind of inches forward up like this. Okay? And if I change the number of time steps here, you can kind of see the steady state solution. Right? So let me change to 25. Okay. And you can finally see the steady state solution. So it kind of starts low right here, and then it kind of gets up to basically the straight line. And that's basically our solution here, okay? Right? And so that's a demonstration of the explicit Euler method here, right? So explicit methods like explicit Euler, are actually very popular because, when we're doing this system here, right? Notice at the beginning, I told you that this system that I wrote down is not a system of equations, right? And so if you'll notice here, I did not use any backslash notation, right? Right, and that's a big deal, right? Because normally when we solve, or up to this point, when we solve our systems, we would do something like A\B, right? And so it turns out, even though the computer is really good at solving linear systems of equations, it's still really slow. And so when you do this A\B, it's way faster than what humans can do. But for a computer, that's still relatively slow. And so when you have the system in this form, when you're just performing matrix multiplication, this is actually extremely efficient, in terms of time. So explicit Euler is really popular for that reason alone, and that you kind of avoid doing a linear system solve, which ends up saving you a lot of time. But then the risk that you run when you do this is that your solution might be unstable. Okay, so any questions on explicit Euler so far? Okay. Chat, let me see. All right, and so that's the explicit Euler. And so, it's great. So, it's great when it works, but when it doesn't work, it becomes unstable, right? And so this should sound a little bit familiar to when we did convection. And so if you remember from convection, we had one other option available to us when we had an unstable solution like this, which is, instead of refining the grid, another thing that we can do is we can just simply change our scheme, right? And so if we changed our scheme from central difference to like forward difference or backward difference, depending on the direction of the convection velocity, we can still end up with a stable solution. Right? And so time marching is the same thing. So in time marching, we can change the scheme here, which you can kind of see at the bottom of this page. And the alternative to explicit Euler is implicit Euler. And that's going to be the subject for the next part of the lecture. So let me go ahead and stop sharing. Let me bring back our iPad here. Okay. And so the next part that we're going to learn is the implicit Euler method. Okay. All right. And so implicit Euler is the alternative to explicit Euler. Right? Okay. You guys, I've been hearing kind of music in the background. Yeah. Yes, if your mic is on, can you please turn it off? Thank you. All right. And so, the alternative to explicit Euler is implicit. And the nice thing about implicit Euler is that, and what you'll see is that implicit Euler is almost always stable. For the problems that we'll be doing in this class, it's technically always stable, but there's ways that you can break it. Never underestimate, an engineer's desire to break something that someone says is unbreakable. But so in reality, implicit Euler is almost always stable. But for our case, we can consider it to be stable. Okay. Okay. And so our starting point for this is going to be our general equation again. So I'm going to do this in 1D just to kind of simplify the math. And you'll see kind of the one kind of change that we do compared to explicit Euler. Right, so I'm going to start with our conservation equation. And so we have our time derivative. Next, we have our convection term. And so our convection term is minus u, partial phi, partial x. And then we have our diffusion term. Okay. And so that's k, partial squared phi, partial x squared, okay, plus q of xi, okay, or q of x, I should say. Okay. And so here's our starting point for this. And so, just like we've always done, we're going to apply finite differences to this guy, both to the time derivative and to the space derivatives in order to turn this into an algebraic expression. Okay. And so let's do the time derivative first. And so remember, for the time derivative, we're going to do the finite difference in time, right? And remember, our time index we put in the superscript and we use n for that, right? And so we have phi n plus 1 at I minus phi at n and I. Okay. And that's going to be divided by the time step size, which is delta t. And then we're going to multiply by the finite difference approximation for the convection derivative, which we're going to do in space. Okay. And for now, I'm just going to use a central difference for the convection term, just because this is just kind of generic for use. We're not sure which way it's going. Okay. So that's going to be I plus 1 and n, okay, minus phi I minus 1 at n, okay, divided by 2 delta x. Okay. Then we have our diffusion term, and our diffusion term we've just been using the same one for this guy. Right? So we have phi I minus 1 at n minus 2 phi I n plus phi I and n at I plus 1, okay, all divided by delta x squared. Okay. And then to this, we're going to add qi, okay, which is going to be our source term evaluated at the x coordinate xi. Okay. Okay. And so this was the starting point for our explicit Euler. And so, what we did was we kind of worked through this and we put all of the phi n plus 1s on the left and all the phi n's on the right. But if you remember, one thing that we kind of had to do arbitrarily was for all of these space derivatives on the right, remember, we had to assign a time index to these guys. Okay. Or in other words, we had to assign a value of n, so either n plus 1 or n. Okay. And so for explicit Euler, what we did was we assigned a value of n, or a time index of n, to all of the, the phi terms on the right. But for implicit Euler, we're going to do the opposite. And so for implicit Euler, we're going to take all these phi terms on the right side and then evaluate them at n plus 1 instead. Okay. Okay, so this would be n plus 1, n plus 1, n plus 1, n plus 1, n plus 1. Okay. And so this kind of changes the nature of our equation pretty dramatically. Okay. But just like we did, in the previous, in the previous, method for explicit Euler, we're going to take all the phi terms that are evaluated at n plus 1, move them over to the left-hand side. Okay. And then all the terms with n as well as all the other terms, so as well as the source. Okay. And so our q values, and we're going to put all of those on the right. Okay. And then from here, I'm going to simplify the expression so that we get kind of one thing, and then that will derive our implicit Euler solution. Okay. Okay, so any questions on this before we start working through the algebra? Okay. All right. And so to kind of simplify this a little bit, what I'm going to do is I'm going to multiply both sides of the equation by delta t. And so this is the same thing that we did for explicit Euler. Okay, and so if we do that, we end up with the following, right? And so on the left-hand side, we have phi I n plus 1, okay? And so this came from our time derivative, and so we left that guy over there because it's an n plus 1 term, okay? Then we have the convection term, and so the convection term is u delta t divided by 2 delta x, okay? And so we have a plus here because it was negative on the right-hand side. So when we moved it here, it becomes positive. So this is phi I minus plus 1 at n plus 1 minus phi I minus 1 at n plus 1. Okay. And then we have the diffusion term. And so the diffusion term is going to be a minus k delta t divided by delta x squared times phi I plus 1 at n plus 1 minus 2 phi I at n plus 1 plus phi I minus 1 at n plus 1. Okay. And this is all equal to phi I at n. And so this came from our time derivative term that we moved over to the right, plus qi. So this is the result of, multiplying by delta t and just, moving all the n plus 1 terms to the left and then all the, n terms to the right. And so just to simplify this so that, we can kind of, start plugging in expressions for this, let's combine like terms on the left-hand side. Okay. All right. And so if we do that, we end up with the following, which we're going to use to in the example. Right? And so first we have the coefficient for phi I minus 1. So we have v minus u delta t divided by 2 delta x plus k delta t divided by delta x squared. Okay. Phi I minus 1 n plus 1 plus 1 plus 2k delta t divided by delta x squared, phi I n plus 1 plus u delta t divided by 2 delta x minus k delta t. Oh, sorry, this should be a minus right here. Minus k delta t divided by delta x squared. So I changed this this plus on this first guy to a minus. Yeah, sorry about that. Okay. Phi I plus 1 n plus 1. Okay. And this is all equal to phi I at n plus qi. So a lot of terms there. Yes, we do. Thank you. I forgot about that. Yeah, so the q term should also be multiplied by delta t. Yeah. Mm-hmm. Yeah, thanks for catching that. Okay. And so this is a basically your implicit Euler system of equations. Or should the implicit Euler time marching scheme. Okay. All right. And so it's a little bit hard to tell, you know, when the equation's in this form. But remember, you know, when we're applying these, you know, when we're applying these time marching schemes, what we ultimately want to solve for is phi at n plus 1. Okay. But the problem with this is that, you know, just like the name implies, you know, we don't have an explicit expression for phi n plus 1. Because if you remember, you know, when we were talking about explicit Euler, you know, when we were, you know, working with that one, you know, we weren't solving a matrix set of equations for that one. What we were solving for, or you know, what we were doing was we were just doing simple matrix vector multiplication, right? And so we said phi n plus 1 is just going to be the product of this matrix times this vector plus another vector. Right? And so that was really easy because that's just, you know, matrix vector multiplication. And so if you compare that to solving like a linear system, you know, that was much easier. Right? And so in this case, you know, we don't have that because, you know, we have kind of multiple phi n plus 1 terms here on this side of the equation. Okay. And so since, you know, in one equation, we have multiple phi n plus 1, since we have I minus 1 and I plus 1, means that we can't, you know, explicitly solve for phi n plus 1. Okay? But what we can do is that, you know, after we apply this to every node in our mesh, what we're going to get here is a linear system of equations. Right. And so even though, you know, we won't be able to solve for it explicitly, if we solve for all of these, you know, all these time marching schemes for every node in our mesh at the same time, then that will give us all the phi n plus 1s. Okay. And so, you know, this, in some sense, this is very similar to, you know, all of the steady state problems that we've been solving for before. Okay. Because in order to solve for this system, we're going to need to make use of, you know, MATLAB's backslash notation, right? And so, you know, these problems, you know, we're basically going to set up the system of equations, get all the matrix coefficients, and then use MATLAB backslash, which is, you know, the real hero of this class, to solve that system. Okay. And so, you know, it'll be slower. And so, you know, there's no doubt about it. Implicit Euler is going to be slower than explicit Euler, you know, but the benefit that you get for doing that extra work and taking that extra time is that your solutions are always going to be stable. Okay. All right. So any questions on this before we go into an example? Okay. All right, so let's redo the previous example, but let's do it with implicit Euler instead of explicit one. And so our previous example looked like this, and so we had partial phi partial t is equal to 3 times partial squared phi partial x squared And, you know, we're working with the same boundary conditions. Right. Okay. And so if we have a grid of 5 points, just like before, and a time step size of 0.1, so this is going to be delta x is equal to 0.25, and delta t is equal to 0.1. Right? What we want to do is we want to march this system forward in time using implicit Euler. Okay, and so for this problem, since it kind of fits into this form right here, I'm just going to basically plug in the values for everything here. Okay, and so if we plug in all the values, in this case we have no convection, so u is equal to 0. We get the following equation, right? And so we have a minus 4.8 vi minus 1 at n plus 1 plus 10.6 phi n plus 1 minus 4.8 phi I plus 1 n plus 1. Okay. And our source term is 0 here, and so this is going to be equal to phi I n. Okay. Okay. And just like before, what we're going to do is we're going to apply this to every interior node in our mesh. Okay. Okay. And so our interior nodes in this case is going to be I is equal to 2, I is equal to 3, and I is equal to 4. Okay. And so when I is equal to 2, we have minus 4.8 phi 1 n plus 1 plus 10.6 phi 2 at n plus 1 minus 4.8 phi 3 n plus 1. And this is all equal to phi 2 at n. Plus, right? And so we can do the same thing for I is equal to 3. Okay. And so those are all the equations for our interior nodes. Okay. And then for the boundary, and then for the I is equal to 1 and I is equal to 5, we're going to apply the boundary conditions for these guys. Okay. And so at I is equal to 1, we have our Dirichlet boundary condition, right? And so we have phi I at n plus 1. It's simply going to be equal to its boundary condition value, which is just 1. Okay. And for I is equal to 5, we have a Neumann condition. And so we have phi 5 n plus 1 minus phi 4 n plus 1 divided by delta x is equal to, I think it was 2, right? Yep, 2. Okay. And so if we multiply both sides by delta x, then what we get is 2 times delta x, which is just 0.5. And so these are all the equations that we have to solve for our implicit Euler. Okay? And so on the next page, what I'm going to do is I'm going to put this in matrix form, and I'm going to show you, how to actually solve this on the first step. All right. Any questions on this? Okay, and so let me go ahead and put this in matrix form for you guys. Okay. And so the matrix form looks like this. Right, and so on the left-hand side, we now have a coefficient matrix, right? So the coefficient matrix is 1, minus 4.8, 0, 0, 0. Right? And then we have 0, 10.6, minus 4.8, 0, 0. We have 0, minus 4.8, 10.6. 4.8, 0, and then 0, 0, minus 4.8, 10.6, minus 1, and 0, 0, 0, minus 4.8, and 1. Okay. And all this is going to be multiplied by phi i's at n plus 1. And so this is phi 1, phi 2, phi 3, phi 4, phi 5 at n plus 1, okay? And all this is equal to the right-hand side. And so that's everything on the right of the equal sign. And so for our first row, we just have 1, which is our Dirichlet boundary. Right? And for the second row, we have phi 2 at n. And then for our third row, we have phi 3 at n. And then we have phi 4 at n. And then finally, we have 0.5. Okay. And so remember, anything with the superscript of n is going to be the solution at the current time. And the thing that we know about the solution at the current time is that we know what the solution is at the current time. Okay. And so everything on the right side of this this guy is known. And so what we have to do from here is we basically have to invert this system using MATLAB, and then that will help us to solve for phi n plus 1. And so I'm going to show you, the example script for this. And so I've posted another example for this, and I'll show you what that's like. Okay. One thing that I forgot to mention in the explicit Euler, example was that after you solve for phi n plus 1. And so after you solve for phi n plus 1, what you have to do is you have to update, the current solution to match that one. Okay. And so the way that works is, once you solve for, this guy right here, this phi I at n plus 1, that now becomes the current solution, right? And so what you can say is, for the next time step, this phi I at n is going to be your newly solved phi I at n plus 1. Okay. And so since you just solved for this, in code, you have to explicitly say that, now my current solution is equal to what I just solved for, because I'm going to need that in the next time step, right? Because every time step, you always need to know, or every time you solve for the solution at a new time step, you need to know what the solution looked like at the last one, right? And so every time you solve for a new one, you have to kind of save that previous one so that you can plug it in for the next step, okay? And I'll show you how to do this in code. So it's it's very simple to do in code. We're just going to simply use our equal sign operator there, okay? Okay. And so any questions on this before we I switch back to my laptop screen? Okay. All right. And so remember, to get this matrix right here, what we used a time step of 0.1, right? And so if you recall, in the last episode, which was 30 minutes ago, was that when we tried to use explicit Euler with the 0.1, we ended up with an unstable solution, right? And so what we're doing basically is we're doing the exact same thing. So we're using the exact same time step size, but we're using implicit Euler instead of explicit, okay? And so the question that I want you guys to think about as I show you the code is that if we're using the same time step size, are we going to end up with an unstable solution? Because if we're still unstable after using implicit Euler, then we did all of this extra work for nothing. Okay, but you'll see that that's not the case. All right, so let me go ahead and switch back to my laptop screen. Okay, and then what I'm going to show you here is this is the implicit code that I've posted. Right, so this is the second sample code that I've posted onto Canvas. Right, and so you can download this as well, and so you can kind of look at it and use it for a future homework assignment. But for now, I just want you to kind of, just to kind of, watch and kind of see what's going on. Okay. All right. And so first thing I did was I first defined, this matrix right here, right? And so that's what this section of the code is. And next I started, this, what this B vector is, which is this right-hand side vector, right? And so, we can't fill in all of it because we need the current solution values here. But I at least could fill in, the top and bottom entries of this, which is 1 and 0.5. Okay. Right. And then just like before, what you see is I've created variables for the solution at n+1, which is going to be sol next. Right. And so this is, what we end up solving for. And this sol cur, this is our solution at n, right? So this is all the phi n values. And then from there, we can start going, right? And so notice how, I initialized the sol cur to be a zeros vector. And so this matches up with our initial condition, which, assumes everything starts at 0. Okay. And so let's go ahead and look at the time marching loop now, right? And so the first thing that you see me do is that you see me, assigning the rest of the values for the B vector, okay? And so the B vector, we need basically the current solution at node 2, the current solution at node 3, and the current solution at node 4, right? And so that's what I'm basically doing right here. Right? And so these segments of code assign the current solution values, i.e. solution at n, to the right-hand side vector, okay? Let me put this enter, okay? Right, and so, because we needed phi2 at n in the second row, what I did was that b at 2 is equal to sol cur at 2, b at 3 is equal to sol cur at 3, and then b4 is equal to sol cur at 4. Right? And so these 3 lines of code are basically the exact, implementation of this. Okay, and so these are going to change in every time step, and that's why we need to update this, within the time stepping loop right here. Right. And then, now that we've had the B vector fully defined, we can go ahead and solve it. And so we can take our A matrix and then do our, magical \B, right? Okay. And then, this line of code here is what I've talked about before. So after you solve for sol next, which is, the solution n+1, you have to update the current solution. And so now the phi n's become, what we just solved for was the phi n plus 1s, right? And so after that, we can plot it. Right? Okay. And one other thing that I think I forgot to point out earlier was that whenever you have an unsteady problem, you have to march it forward with a loop, right? Because because we're going to be solving it one step at a time, we need to loop it over all the time steps that we're going to solve for. Okay. And let me solve this for 25 time steps, just so that you can see what it's like going forward. Okay. And so remember, when we did explicit Euler with a time step of 0.1. We ended up with an unstable solution. And so let's see what happens when we do it with implicit Euler. Okay. And so you can see with implicit Euler, even with the time step of 0.1, we end up with a stable solution, right? So eventually everything kind of converges onto the straight line, and we don't have those weird, Krusty the Clown, Simpson head, oscillations like we did before, right? So you have just a nice smooth curve, right? And so that's good, right? And so, to do implicit Euler, we had to do quite a bit of extra work, or maybe not us, but MATLAB had to do a lot of extra work because remember, instead of just doing simple matrix multiplication, what we're doing is we're solving a linear system of equations with backslash, right? And this is a lot more costly in terms of time and in terms of memory than simply just doing matrix multiplication. Which is what we did in explicit Euler. And so it's expensive. So implicit methods are expensive. Because you can imagine, we're not only solving this linear system just once. We need to perform a linear system solve at every single time step, right? And so, this one's not so bad because we only have 25 time steps, but you can imagine, how tough this would be if we were solving this for like 1,000 time steps, right? And so, imagine taking your, taking your 2D codes that you've worked with, up to this point and try running it 1,000 times in a row. And that's just one unsteady simulation. Okay. And so it's unsteady problems can get pretty expensive. And so, what some people were telling me last year for the final project for this class, when they were running their final project, which was an unsteady problem, sometimes it would take them an hour just to let MATLAB chug through all of the calculations if they picked if they put implicit Euler, right? And so it's not a trivial decision. And so you have to be kind of really careful about what you kind of pick for these guys, right? But all that extra work goes towards something nice because if you use implicit Euler, then you basically don't have to worry about unstable solutions at all, right? And so it's a trade-off, just like we talked about in convection, right? And so you can go with an explicit Euler, and end up, try to kind of risk it and try to solve for a quick solution, or you can kind of do the extra work, do implicit, and you don't have to worry about unstable solutions at all. Yeah, 1 hour for just one simulation. It took them 1 hour. Mm-hmm. Yeah, so it's a choice. It's a real trade-off that you kind of have to make. If you feel confident in your implementation and you're confident that you run it once for an hour and it's going to be correct, then that's great. But if you think you're going to have to run it several times, you can't afford to run it, let it run for an hour just to find out that you had some error in your code, fix the error, run it for an hour again, find another error, fix it again. So it's a real trade-off that you kind of have to think about. All right, any questions on this before we start to get into 2D problems? Okay. And so I will say that I haven't looked at every single commercial code out there, but I have seen quite a bit of them. And and I will tell you that most codes actually, believe it or not, they use explicit methods, right? And so they don't use explicit Euler because explicit Euler is kind of the simplest one that you can do, but there's more sophisticated explicit solutions out there, which have better stability properties, but still you still avoid having to solve a system of equations, right? And so most codes out there are actually explicit, and then they kind of rely on the users picking a small enough time step size in order to kind of make it work. How many are left after 5? So after doing that, I convinced that student to do an explicit Euler solution, And then, he was able to fix the project from there. And so, actually most people finished the project. I think, pretty much everyone was able to get a working code by the end. So, and most people ended up using an explicit code just because it's faster that way. Okay. And so let's talk about 2D problems. And so far we've just done unsteady problems in 1D, but we can do unsteady problems in 2D too. And so this is kind of the part where we kind of put it all together. And so if you kind of remember the equation that we started with at the very beginning of class, now we can basically solve everything that we can, everything possible that we can in finite difference. Okay. And so this is going to be unsteady, convection, and diffusion in 2D. Okay. And so in 2D, nothing's going to change. And so we're going to apply basically explicit Euler and implicit Euler exactly the same way as we did before. It's just that now there's going to be a lot more terms that we have to kind of worry about. Okay. And so let me start with our conservation equation. And finally, everyone can kind of be together in the same place, right? And so we start with our unsteady term, right? And then we have the X convection term, and then the Y convection term, and then we have our diffusion term. Okay. And then we have our source, right? And our source can be a function of X and Y, okay? And so finally, we've been working up to this point, throughout this whole class so far. The gang's finally all here, right? So penny, chip, use napkin, convection, unsteady, diffusion, everyone's in the party now. And we can kind of finally discretize this guy all together. Okay. And so let's go ahead and discretize this using finite differences. And then, I'm going to do it for an explicit Euler scheme. Okay. All right. So let's start with the time derivative term. Okay. So let me go ahead and color code this just so that we can keep track of everything. Right. And so the time derivative term, we're just going to apply just our usual finite difference in time for this, right? And so it's going to be phi I, comma j, n plus 1. My iPad will cooperate. Okay. Minus phi I, comma j at n, all divided by delta t. Okay. Next, we have our convection term. And so our convection term, we're going to do a central difference scheme for this in space. Right? So we have phi I plus 1, comma j, minus phi I minus 1, comma j. And both of these are at time index n because we're doing an explicit scheme here. Okay. This can be divided by 2 delta x. Next, we have our y derivative term. And so our y derivative term is going to be v. And I'm going to again apply a central difference scheme in y. And so this can be phi I j plus 1 minus phi I j minus 1. Okay. And once again, since we're doing explicit Euler, we're going to evaluate these at time step n. Okay. And this is all divided by 2 delta y. Okay. Next, we have the diffusion terms. Okay. So let me start with the x diffusion term. And so this is going to be equal to k times phi I plus 1 comma j minus phi I comma j, or minus 2 phi I comma j plus phi I minus 1 comma j. Okay. Let me clean this up a little bit right here. This should be I plus 1. Okay. And all of these are evaluated at time step n. Okay. And of course, all divided by delta x squared. Okay. And then we have the y derivative term. Okay. So it's going to be a plus k, and then phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1, all divided by delta y squared. Okay. And again, all this is evaluated at time step n. Okay. And then finally, we have our source term, which is q I j. Okay. All right. And so a lot of terms and a lot of frustration with the iPad later. We finally have, everything here. Yes, that's before the orange here is an equal sign. Yeah. Mm-hmm. Okay. All right. And so what we can do from here, so now that we have, all the terms written out, is we can, combine like terms, move terms around, and, simplify this so that we can, more easily apply this, right? And so just like we've done in the 1D cases, we're going to put all the n plus 1 terms on the left. Okay. And so in this case, we only have one of them because we have, it's an explicit scheme. And then everything else we're going to put onto the right. Okay. Okay. So any questions on this before, I start moving stuff around? Right. I'll give you maybe one more minute because it's a lot to write down. Okay. And so let's go ahead and move stuff around, right? And so I'm going to skip some of the steps a little bit just because it's it's kind of a lot of algebra, and so I'm going to kind of skip to the final result. But you can go ahead and verify this, and all the steps are written out in the lecture notes as well, so you can look at that. And I'll do one thing that I did very similar to what I did in the previous one is I'm going to multiply the entire equation by delta t. And so after multiplying by delta t and then moving, all the terms according to that, we end up with the following explicit expression. Right? And so on the left-hand side, we have phi I comma j at n plus 1. Okay. This is going to be equal to, first is going to be our left neighbor. And so this is u delta t divided by 2 delta x plus k delta t divided by delta x squared. Okay. And so this is phi I minus 1 comma j evaluated at time step n. Okay. To this, we're going to add a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared. And this is phi I plus 1 comma j at time step n. Okay. plus v delta t divided by 2 delta y plus k delta t divided by delta y squared. And this is phi I j minus 1 evaluated at time step n. Okay. And then we have a plus minus v delta t divided by 2 delta y plus k delta t divided by delta y squared. And this is phi I j plus 1 at time step n. Okay. And then plus minus 2k delta t divided by delta x squared and minus 2k delta t divided by delta y squared plus 1. Okay, so that plus 1 comes from the time derivative on the right. Okay. So this phi I comma j to the n. This will be times q I j times delta t. And so it's kind of a monster, right? So it's kind of a big chunker of an equation, right? So there's lots of terms going on here and lots of lots of things to do. Right? And so this expression right here is our explicit Euler time marching scheme for 2D convection diffusion. And so if you have a problem, that's 2D and it has convection and diffusion and it's unsteady, I think the best way to go about this, when you're first starting out, is to kind of take this expression right here and just, plug in, the values for u, delta t, delta x, k, u, and v, right? And then what you'll get is a kind of all these terms in parentheses right here will just turn into constants. And then, you can, just compute those in code, basically. Okay. And so I have an example for this too that we can do in the code, but let me write out the, the system on hand first, just so you kind of know what's going on. Okay. And make sure that you have this equation here written down, because if you have this written down, it'll help you kind of follow the code along easier too. But before I launch into that example, are there any questions on this here? Okay. All right. And actually, before I jump into the example, let me kind of make one quick note here. And so remember this expression here, this is going to apply for all the interior nodes. And so for the boundary nodes, remember we're going to use boundary conditions for those as well. Okay, so just like before. So even though our our equation here has kind of grown in girth, doesn't mean we're going to change how we do things. Right? Okay, so let's do an example. And I'll start this example here, and then we'll probably finish it up next week after the midterm. And so for this example here, we have a 2D situation. And so this 2D situation, we have something looks like this, right? So we have phi is equal to 50 up top, phi is equal to 50 right here, phi is equal to 25, and phi is equal to 25, okay? And so we have Dirichlet conditions all around. And let's say that we're going to have 30 nodes in each direction. Right? And so, with 30 nodes in each direction, we have basically 900 nodes in total. And so this is going to be, way too much to solve by hand. Okay. And then the equation that we want to solve for is the following. Right? And so our equation would be d phi dt plus 50 d phi dx, right, plus d phi dy is equal to 3 d squared phi dx squared plus d squared phi dy squared plus and actually let's ignore the source. So let's say that we don't have any source term here. Okay, and so this is our equation. Okay. And so from this equation, let's go ahead and pick off some of the parameter values, so we can just kind of plug it into this expression over here on the left. Okay, and so from this expression, we can see that u, which is our x velocity here, is going to be 50, right? So we kind of pick that off from the partial phi partial x term. V in this case is going to be 1, and so we pick that off as the coefficient for d phi dy. And k is equal to 3 because that's the diffusion coefficient. Okay, right, and so that's that's all those parameters. And then in addition to that, we also are going to need the grid spacing delta x and the time step size delta t. Okay, and so for delta x, let's assume that it's going to be 1, and so let's assume that the length of these sides are 1. And so our delta x here is going to be 1 divided by 30 minus 1, okay? And to make this stable, remember, because we're using an explicit scheme here, so we run the risk of running unstable. Let's use a time step size of 0.0001, okay? And so when I was doing this example here, I had to reduce the time step size by this much in order to get a stable solution. And let's run it for the number of time steps equal to 250, okay? All right.
What does delta x equal again?
So delta x is going to be 1 divided by 30 minus 1. And so let me go ahead and divide that. And so this is going to be 0.0345. Right. So I didn't actually compute it because I computed it in the code, but that's its exact values. Okay. And so, with all these in mind, we're basically going to implement this kind of chonker of an equation into the code. Right? But, since we're kind of running out of time, I think I'll save that for next time. But, I will kind of, remind you kind of the general form that we kind of expect for explicit Euler schemes. Because remember, when we run explicit Euler, we should not get a linear system of equations. What we should get is, something that we can just solve by just doing matrix multiplication, right? Okay. And so what we should get is something that's equal, like phi I comma j at n plus 1, okay? N plus 1. This is going to be equal to some a times phi I comma j at n, okay, plus b. Okay. Where this a right here, this a is a matrix of coefficients. It's a matrix of coefficients that's determined by, this chunker of an equation, right? And so it's determined by a time marching scheme. Remember this phi at n, this is known, okay, because it's the solution at the current time, okay? And this b here is just whatever's left. Okay? And so usually what goes in here are like the boundary conditions and the source term. Right? And so when we pick this up again next Monday, you know, I'll show you the code and I'll show you basically how this this guy is implemented right here. Okay. All right. So thank you guys for tuning in today. You know, remember the midterm is on Wednesday. So you know, if you want to come to the Zoom call and ask questions there, you're welcome to do that. But you know, it's not required. And so if you would rather take the exam, you know, in kind of privacy, that's okay with me. The only thing is, you know, just make sure you submit the exam by 7 p.m. And so I'll send out an email tomorrow with kind of, you know, more of these instructions. And then, you know, Wednesday we'll take the exam. So thank you guys for tuning in today. You know, best of luck studying. You know, if you have any questions, you know, leading up to the exam, definitely shoot me an email or shoot me a Discord message. You know, and I'll see you guys on Wednesday. Solution to homework 3 will be posted at midnight tonight. Yeah, you can ask questions on Discord as well. Yes. Mm-hmm. Yeah, both before the exam and during the exam. Mm-hmm. Thanks, guys.
Professor,
Yep, what's up?
could you scroll up to the colorful equation?
Oh, yeah.
Thank you. Yeah, so if Canvas is closed by that time, you can just email me your responses. Try to get the short answer ones typed in at least, and so you know those you can type directly into the browser. But for the ones you work out by hand, you can just email them if it's after 7 p.m.
Okay, sounds good. Thank you.
Mm-hmm.
All right, have a good night.
Yeah, you too.